me again, Antonio Faraone, one of the instrument scientists for the Neutron Spin Echo spectrometer. Can you hear me well?
Yes.
Yeah. Okay. So the second lecture today is an introduction to dynamic neutron scattering, and essentially the goal of this lecture is to give you all the concepts and information that you need to understand the third lecture about spin echo. So you will need to learn about the role of thermal fluctuations, why we are deciding to use neutrons as a probe to investigate this thermal fluctuation in nanoscopic range, understand space-time correlation function, the concept of length and time scale, static, dynamic scattering, elastic, quasi-elastic, and inelastic scattering, and finally understand the concept of instrumental resolution and energy window. If this looks like a lot to you, it's because indeed that's the case. So I will not have the time to go in detail. However, you have some reference material that you can access. So I'll try just to give you to explain to you the concept of all these points, and you can look at your own time using the reference material about the details. So I'll start with a question, and the question is this water moving? Is this water moving? Yes or no? Yes, I saw one head shaking at least. Why is it moving? It doesn't look moving to me. Oh, but maybe a little bit of shaking. Sorry? Temperature, yes. At the molecular scale, water molecules diffuse, rotate, vibrate. So a visual indication of this is the Brownian motion. I stole this video from, from YouTube. Okay, the Brownian motion that you can visually see on a microscopic length scale is an indication of the motion of the molecules surrounding the Brownian particles. But you cannot actually see the motion of the solvent. You just see the effect of it on the Brownian particles. So, but what if we really want to look at the dynamics at the molecular level that happens because of thermal fluctuation? Okay, if you are a simulation guy, you can say, oh, I can see that with simulations. And this is an example of a nice simulation of water molecules. You can nowadays have simulations also of a more complex system. This is a soft matter workshop. So you can see that you have simulation about polymer dynamics, membrane dynamics, protein confined within nanoparticles. But these are simulations. How do you access, how do you obtain experimental information about the dynamics, the thermal motion of the system? Generally speaking, the techniques that we use are called spectroscopic techniques. Those spectroscopic techniques, like dynamic scattering, dielectric spectroscopy, the way they work, very generally, broadly speaking, is they measure the response of the system as a function of the frequency, either of a stimuli or the light, absorption, different methods. So these are essentially based on a spectral analysis of the system. Spectrum means as a function of frequency, and that's the crucial word there. Again, these methods do not need to stimulate the system. They do not take the system out of equilibrium. Generally speaking, these are fluctuations that take place in your system just because of the thermal energy of the system. Why are these fluctuations important? Bottom line is because the way your system dissipates a fluctuation is the same way the system responds to an external stimuli. The same diffusion coefficient that controls the Brownian motion of your particle is the same diffusion coefficient that dissipates a gradient of concentration. So if we want to learn how your system responds to a system, to a stimuli, we can learn how the system behaves in terms of its fluctuation, thermal fluctuations. Here, as I mentioned already, the case of diffusion. Another example is related to sound wave propagation. The way sound wave propagate is the same way as the system dissipates density fluctuations in the system. So why neutrons, though? Why do we want to use neutrons? As I said, there are simpler, more economic ways to obtain this kind of information. So some of these concepts have been already introduced in the previous lecture, but I will reiterate. Neutrons are sensitive to light atoms, in particular hydrogens. You can use isotopic composition to make things visible or invisible to neutrons. They have high penetrability, so you can study your system where at high temperature, low temperature, in magnetic environment, you have large flexibility in that case. They also have a magnetic moments that make them a probe of choice to investigate the magnetic system at the nanoscale. However, again, this is a soft matter school, so for the time being, we will forget about it. Another unique aspect of neutrons that we will discuss later is that they can access the single particle dynamics of hydrogen atoms, looking at the incoherent scattering. This is a very important part. However, we will not really dwell with it too much in this school, but given the relevance of it, I need to mention it here. So, what does make neutrons unique? And because of that, let's continue. These are all things that we have highlighted in the previous section. What about the length scales? What is the main difference between neutrons and light? It was said before. Why we use neutrons to study system at the molecular scale, and we do not use visible light to study system at the molecular scale? And the answer is probably in the slide. Exactly. The wavelength associated with the neutrons, with the wave associated with the neutrons, has a length scale of angstrom and nanometers. So that's appropriate to investigate system at the nanoscale. So this is why we use neutrons or X-ray to study the structure of system at the molecular scale. But here we are not talking about structure. What we are talking in this lecture, if it is not structure, is dynamics. And what is the parameter, the physical parameter that is associated to the dynamics of the system? The structure associates to momentum. What is the dynamics associated to? Time or
energy.
Sorry?
Energy.
Energy. Time and energy is actually both good word because they are connected by a Fourier transform. So that's the key. So we are going to look at what are the typical energy of a neutrons that have the wavelength that we are interested with, that is between, let's say, 1 and 10 angstrom. If we do some calculation, we use the equations by de Broglie that were already presented in the previous slide, we realize that basically neutrons have an energy that matches more or less kBT. And whereas if we do X-ray, the energy is way higher. So therefore, when neutrons interact with the sample or with the motion of the sample, they exchange an amount of energy that is comparable to the actual energy they come in. And therefore, it's possible for us to appreciate that amount of dynamics. That's why neutrons are good probe to study molecular dynamics. And bottom line, they are comparable energy to the motion. Is this clear? So as a consequence, if we try to draw up a diagram of the length scales and time scale the different methods, experimental methods can probe, we might come up with something like this. You will see different ways of doing the same graph. Hopefully, this one I did capture the main points. But bottom line, what you have is that you have a static measurement to study the structure. And we have a small angle scattering both of light light scattering here, small angle scattering, X-ray and neutrons right there. You have diffraction to study the atomic length scale. You can use visible light nowadays to do amazing things to a certain range, but not to this range. But again, if you are talking about the spectroscopic methods to study dynamics, you can use dielectric spectroscopy, NMR, rheology. But if you look here, you see that I have confined these techniques in this range. Why? Because they give you information about the time scale of the motion, but they do not provide information about the length scale of the motion. They do not provide information about the geometry of the motion. Sometimes you can figure it out, but you have to make modeling assuming a certain process is what you are seeing. With the scattering methods, you have both information about the momentum and the energy exchange that gives you information about both the time scale of the motion and the geometry of the motion. And that's what we are going to detail later. If you have a light scattering, it's very powerful. You can scan a large amount of length scales with it, but you are confined in almost thermodynamic limits of length scale. X-ray techniques are also very powerful. They have the right length scale to study system of molecular motion, and they are getting more and more powerful every day. But still, they have difficulties to study the dynamics of the system at the nanoscale. Nanoscale, I mean picoseconds to nanoseconds, to nanoseconds to hundreds of nanoseconds time scale. That's still a range of dynamics where neutron scattering techniques, spin echo, and backscattering that you will hear about the last day are basically the unique range. So that's why we invest lots of money in neutron spin echo, and that's why you are here. Yes, please.
Is there a particular reason that spin echo has the shape of that?
Yes, it is. I don't want to give you detail, but it's because the way it works, the momentum and energy range, so the energy scale that can be probed depends on the wavelength. And the wavelength is what defines the length scale that they can be probed. So both those are connected, and that's why it's selected that way. But that the details will probably come up in the next session. But good question, thank you. So how do we do this in practice? Again, this is just reiterating what was said before. In general, with a scattering experiment, you shoot your probe particles with a well-defined energy and momentum and a certain flux on your sample. Then, because of the dual nature of these particles, they interact with the sample and come out, and within certain approximation, we can still imagine them as a particle coming out. The scattering experiment essentially consists in measuring the probability that these probe particles have exchanged a certain energy and momentum with the sample, and therefore will be detected at a certain scattering angle or with a certain energy. And the main parameters, again, are the exchange wave vector, the momentum exchange between the probability that a certain momentum has been exchanged, that gives the Q, and the probability that the sample and the neutron have exchanged energy E between the sample and the neutron. So E is the keyword. What's the difference with the previous lecture? You remember?
Energy.
You don't have the energy. In the static scattering, you do not analyze the energy that has been exchanged. You just count how many have changed the direction to a first approximation, and that's how you obtain information. Here, you count as many as also the energy. So with static scattering, what you measure, it was mentioned, was the differential scattering cross-section, d sigma to the omega. Here we do the double differential scattering cross-section, the probability that the neutron has exchanged the momentum as scattering in an angle omega, and that's exchanged an amount of delta E of energy with the sample. Okay? Now, I have to give you a little bit of word of caution. Here I will use delta E, indicating the difference between the energy of this scattered neutrons and the incoming neutrons. That's the key. However, people are lazy when they write paper. Instead of E, of delta E, they might use E. Sometimes they use H bar omega. It's the same. Sometimes they even avoid to write the H bar. So please don't get confused. It's all the same thing. It's always the energy exchange between the neutrons and the sample. That's the key parameters. Okay? All right. So this is all good. We have prepared our setup, but out from that, we extract information about the sample dynamics. That's actually the goal. This is a little bit a detail that I do not have the time to go in. It's related very much to the way neutrons interact. There is a lot of physics going into, but let me just give you the main information. As it was said before, the way the neutrons interact with the nuclei can be described by a single parameter, that is the scattering length, Bi. So we can imagine that when a beam of neutrons interacts with the sample, each nuclei in the sample acts as a source of a spherical wave. And then you have to keep in mind that the energy needs to be conserved. You keep in mind that the interaction between the neutron and the nuclei is a small interaction, is a small perturbation. This is words to say that when you do the mathematics analysis, you can stop at the first linear term. Without getting into these details, this is essentially what you get. You get that now your double differential scattering cross-section that you can measure is related to the position of each atoms in your system at time 0 and time t. So let's go a little bit more in detail. This is the equation that we're going to use, but I'm not going to explain the equation, but I'm just going to go through the elements of the equations. That's the only thing you want to know. So the double differential scattering cross-section provides information between the spatial time correlation between a couple of atoms, 2 atoms at 2 different times, not 3, not 4, just 2. That's what you can get. The Q, that again is the momentum exchange or the exchange wave vector, that is something that we can control, we can measure, provides a length scale at which you are probing this interaction. If this Rm over Rn, the distance between the atoms that we probe is too small or too large related with respect to Q, then we will not obtain information. So we can obtain information in Q to probe different length scales. Is it clear, this concept? We use Q that essentially, in most cases, is just changing the scattering angle to probe the motion at specific length scales. All right? So that's how scattering methods and neutron scattering in particular obtain information about the geometry of the motion. It's by varying Q. Then the other element is that the powers of scattering of different atoms is given by these scattering lengths that are information, there are quantities that are tabulated. So these are the 3 ingredients that we use to understand our experimental result and relate it to the dynamics in the sample. Okay. Finally, and this is mathematical detail, once again, the connection between the real space, real time sample dynamics to what we measure is a Fourier transform. It's a Fourier transform in time. So actually, this is the mathematical details that I'm going to discuss in the next few slides. But essentially, what I want to say is rather simple. I want to say that I want you to remember that this quantity that we measure, the double differential scattering cross-section, that is a measurement that happens in Q and E. Those are the two variables that you measure, you control with your experiments, are related to a double Fourier transform in space and time to the real space and real time behavior of your sample. Okay? So again, you have this double Fourier transform. And then there is, I want to just go over a few names that you're going to hear. If you work in the Q and E domain, you call that quantity dynamic structure factor. And you are taking out experimental details. The dynamic structure factor is the way your system will respond. So it's an information about your sample. If you decide instead not to do the Fourier transform in time, and you stop with the Fourier transform in space, you call that intermediate scattering function. It's actually the same information content on your sample, but we call it different. And this in particular is relevant because that's the quantity that spin echo measures. And you will see that later. But again, yes?
It's a small n.
Okay, so this comes later. This is what I said is the function that describes the sample in real space and real time. So there are different ways that you can describe the dynamics of your sample in real space and real time, different way that you can weight different factors. So here n stands to neutron weighted. But because there are, the most common are S and C. And I will explain soon what it is. But basically the n there means the way neutrons see the motion in your sample in real space and time. Okay?
I have one question.
Sure.
We have a case where n and m is same, where we are looking at the same particle as a function of time.
Yes. It's a little bit, it's again, of course, it's an approximation, but within certain, in certain case, it's a very good approximation when n and m are the same. And I think I'm going to get there very soon. Just this is basically a summary. The dynamic structure factor describes correlation between two atoms, two scatterers at two different times. ISF, intermediate scattering function, SQ omega, dynamic structure factor, contain the same information. Remember, the ISF and the dynamic structure factor are properties that you can describe are inherent to the system. You can write them down for a system. You can calculate from molecular dynamics simulation. And then you can measure with neutrons. But it's not necessarily related to the neutron scattering measurement. You can measure it with different techniques. And as I was hinting before, most of these dynamic scattering measurements work in the energy domain. However, spin echo or, for example, X-ray photon correlation spectroscopy work in the time domain. What's the technique that works in the time domain and uses visible light? Dynamic light scattering, DLS. You can also call it PCS. Sometimes that's our name. So now we are going to get a little bit into the detail. This function here that describes the sample in the real time and space is called Van Hove correlation function. And it represents the probability to finding a particle at position Rn at time t, given that the same or another particle was at time 0. And again, it provides a very powerful framework to interpret the dynamic scattering measure. So bear with me a little bit, because I think this will become clearer soon. Yes?
So when you say that you can calculate the intermediate scattering function and the structure factor from, for example, like an MD simulation, strictly get the Van Hove correlation function and then just take Fourier transforms?
This is more a technical details. I believe that's the way that is most commonly done, but I wouldn't be 100% sure that there are no other algorithms that you could use. But yes, I would say that's the most common way that you do that. So now we have to introduce or reiterate a concept that was introduced before, but we're going to look at it in a quite different way. So as it was said before, the scattering length of a nuclei depends on the nuclear spin state, or more precise, the relative orientation on the neutron and nuclear spin state. Is that clear? So what happens is that basically this B will depend on the nuclear spin orientation. Now, do you think, in most cases, both the neutron spin direction and the nuclear spin state are random in the system. There is no correlation between them. And the nuclear spin state is not correlated to the position of the atom in real space. So that means that this average, do you know what this symbol means? Maybe I should have introduced before. It's an ensemble average. So yes, it's the expected value. So we average out among all the possible position and configuration of your system. But since there is no correlation between essentially the scattering power and the position of the atom, we basically break down this into two averages. Now the average is here and there. Why is this important? Because this average, we can make it as long as we know what is the atomic content in your sample. So this allows us, and I skip all of this, to realize that our signal can be divided in two terms. One term relates to the different position of a couple of atoms at different times. And one term that is the incoherent scattering, that was the background of your small angle signal, it relates to the different position of the same atom at different time. That's where the n is the same as you were saying before. So we call this the coherent term and the incoherent term of your system. So the coherent terms relates to different position. The incoherent term is the same atom at two different times. Which of these two terms give you structural information? The coherent term. Would the incoherent term give you structural information? No. The only thing that will give you is how many of those incoherent scatters are. However, it gives you information about the single particle dynamics in your system. Now, basically, we also see that the weights are different. So which nuclei, which atom, has a very large incoherent scattering cross-section? Hydrogen. Remember, it was introduced. Hydrogen is a very large incoherent scattering cross-section. So within certain approximation, in certain case, if your system contains lots of hydrogen, you don't get structural information, but you can get information about the single particle dynamics of the hydrogen. And this is basically weighted by these factors here. So these are just definition for those factors, but this is probably, again, the most fundamental concept. So we can interpret the results of our dynamic scattering measurements in terms of this Van Hove correlation function. And we can call the collective Van Hove correlation functions the probability of finding a particle at position r, given that the same or another particle was at 0 at time 0. In the limit of time 0, you get the particle distribution function. That is what you get with diffraction. With incoherent scattering, you get the self-correlation function. That is the probability to find a particle at time t at position r, given that the same particle was at 0 at time 0. And that's probably, so these are the most common G that you will see. Is either GC or GS, or G self or G collective. But again, in neutrons, you usually get both, and you try to separate them, or try to prepare your sample in such a way that one is dominant, so that you can forget about the other. All right? So I think I'm running quite late, but let me try to hurry up in the next 10 minutes. Now, all of this is a framework that works pretty nicely. It's pretty intuitive, I hope, in the case that you're looking at nuclei and atoms, so at the atomic length scale. However, once again, we have a soft matter workshop, and we tend to work in the tens of nanometer length scale. We tend to work in the sense limit. So without going into the details of the math again, you can look at it later with your pace. I just try to show you how we move from that length scale to a formalism that it's easier to deal with if you work in the sense limit. Because if you are doing soft matter, most likely you will work in the sense limit, and the 3 experiments you're going to do in the breakout group work in the sense limit. So essentially, in the sense limit, you are dealing with large particles, and you're working with the low spatial resolution. You look at that 10 nanoseconds. So the first step that you do is you consider your macromolecules. Since all of you know about proteins, even though some don't know about polymers, I am drawing some sort of a map. And I consider the center of mass of the map, and then every scattering center in the protein the position can be related to the center of mass. That's pretty simple, right? Then if I write again the equations again, now I can break it up, and I see that I both have the center of mass and the relative position of the scattering with respect to the center of mass. So then again, I just break it up, so I have degrees of freedom related to the center of mass and the relative position to the center of mass. And then I have to sum the scattering centers that belong to a certain macromolecules and sum among different macromolecules. Okay, that's all I'm doing. Now, the crucial part is that now that I have separated a part of my equation that relates to the relative position to the center of mass, I can use the formalism that is being used in SANS. I'm in the low resolution limit. So instead of having the granular view of each scattering center being a nuclei, I can go and do an integral, as is being done in SANS. And instead of considering the scattering power of each single atom, I consider the scattering length density of groups of atoms put together. So that's how now I have this integral over the volume. The volume is this macromolecular scatterer. And instead of having B's, I call this the rho of I. That's the scattering length density that was introduced before. And here I have still something that is a sum, because now it's the center of mass. There is also an information about the relative position of the different macromolecules scattering and their center of mass. So now that I have this, I'm sorry, this is a little bit too detailed, but basically I can do some math, or basically I can consider that some of these quantities that are all bundled up together in this equation, they are actually not correlated between each other. So I can make simplification because of that. Essentially, what I'm saying, do you think that the orientation or relative movement of the center of mass of one protein is related to its distance to another protein? Yes, but we pretend no. You had to simplify somewhere, right? but you are correct. I mean, but if we assume that the concentration is low enough, that each protein is so far enough from the other one, then you can say the correlation is very weak and you can neglect it. If you are in a concentrated system, you cannot do it. But if you work out this in this way, you can realize that essentially you can probe either the, that you can probe if you are, for example, in a case where the concentration is very low, you do not have correlation between the different motion of the same nanoparticles, but you can observe the motion of the shape or relative orientation of the nanoparticles. That's how you get to the internal dynamics. And the function that you actually work with is essentially the same form factor that was introduced before, but now is a form factor that depends on time. It's a relative position of structure organization of the nanoparticles at two different times. How does it change with that? That's the function you're going to get here. Now, I'm not going into the details. As I said, there is a lot that are sweeping under the rug, but you can look at it more carefully at your own pace. But essentially what I'm saying is that within certain approximation, we can see that your technique can give information about the conformational motion of your macromolecules. I'm talking about proteins, but also polymer changes, and you can imagine it as a conformational motion of the different chain. The membrane example that was stated before can be considered as the conformational motion of the membrane itself. The center of mass of the vesicle stays fixed or moves too much more slowly. So that's how you get that. And these are the kind of equations that you use. Conversely, and that's also very important, is that if your particle is spherical and is rigid, do you see any internal dynamics? No, because if it's rigid, by definition, there is no internal dynamics. So what you get there is only the information about the relative motion of your particles, so essentially diffusion and things like that. So this is trying to explain to you how, from a formalism that is based on scattering cross-section, we get to a way that allow us to study conformational dynamics and diffusion behavior of large objects. And this relates to the concept, the second last concept, there is a length scale in our system. So this is how more or less a static pattern will look like for a typical soft matter sample. Very general. You will have lots of scattering at small angle, so a low Q that comes from the correlation within your nanoparticles, or your macromolecules. At some point, you get to the incoherent background, where there are no more correlations at that length scale strong enough to give a strong coherent signal, and your incoherent scattering will dominate. If you go even higher Q, you might have correlations between atoms and their motions. So, for example, I don't know if it will be talked about by Michi, but even in your lipid vesicle, if you look at the correlation between the tails, the fact that they are somewhat arranged in an organized way will give you a peak here. Okay, this is the static sketch picture. How does that translate in a dynamics picture? So, okay, if you are a very low Q means large or small distances? large, very large distances, the only thing you can see is the large-scale diffusion of the objects. Now, when your Q increases and you start to get a length scale that match the size of your macromolecules, then you can start seeing rotations or shape fluctuation. Then, where the incoherent scattering is dominant, and that depends on Q, you will see the self-dynamics. And eventually, if you are doing molecular glasses and you look at this peak, you start seeing molecular and atomic correlations. Okay? So that's something that you really need to have in the back of your mind when you do an experiment to understand what kind of dynamic information you are obtaining. All right? So I have 2.5 minutes to teach you a few more names. This is just names, so not too bad. So I spoke about dynamic scattering, and I told you how you prepare your experiment in a way, how you prepare your experimental setup, how you interpret it, but this is how you look. How it will look. First of all, you usually look at a specific Q, at a specific scattering angle, and then you basically plot how many neutrons have exchanged a certain amount of energy with your sample. You can measure it. You just count. And very generally speaking, you will get something like this, where you have a central peak that is rather broad. And then you have some side peak that we call inelastic scattering peak. So why broadening? Broadening means that it is broader than what you would obtain if you put in your instrument as a sample something that doesn't move. Even if you put something that doesn't move, you will not have an infinitely sharp signal. You will still have a finite size signal. There is still going to be a certain amount of energy that it will be exchanged. That's what we call the instrumental resolution. Is the response of your instrument is to something that doesn't move. That is very important because that basically limits the range of dynamics that you can probe. So remember, instrumental resolution. And then quasi-elastic broadening means that if you put a sample that moves, you actually see that this width is larger. And when I say move, remember, it's all qualified at that length scale, because something might not move at a certain length scale, or the movement will be negligible at a certain length scale and becomes important at another length scale. And so this is the quasi-elastic broadening, and then you have the inelastic scattering. So usually what we talk about is full width at half maximum to define how broad it is. So elastic scattering is by definition the amount of scattering that is limited by its resolution limited. It's basically just centered at 0. Static scattering is the total. So what about inelastic and quasi-elastic? So inelastic scattering is caused by harmonic motion in your system, vibration, where you have a certain frequency associated with the motion. So sound wave propagation, that kind of things that gives you inelastic peak. There is a specific energy associated with that motion. Instead, the quasi-elastic scattering is related to relaxation, random motion. It's where there is not an harmonic signal in your system. It's just the system moves from a equilibrium position to another equilibrium position. Typical example is diffusion. So typically when you have relaxation in the energy domain, you have a Lorentzian function. In the time domain, you have an exponential decay. That's the most simple. For inelastic, you will have an oscillation like this. For spin echo, you are lucky. You can forget about this. We are not going to discuss about that. So we'll just focus on relaxation. okay? So as we change Q, as we go from Q that is large to Q that is small, would you expect the dynamics to get slower or faster? Slower, because if you look at larger length scale, usually processes are slower. So things will look like this as you change Q, going from low Q to high Q. And remember, their resolution limit will tell you what is the maximum time scale that you can probe. I think essentially this is it. I'll let Michi go from here. These are details about the resolution, but maybe I can pitch in for it. So as we build instruments and we want to have better and better resolution, that means we want to probe longer and longer length scale, we realize that to do that, we have to compromise more and more on flux. So basically, to have a good resolution, you basically have to define more and more precisely the energy of your incoming neutron, and more precisely define the energy of your detected neutron. That means that you will have a smaller and smaller detection count rate if you do that. So that's basically, there is a theorem essentially that limits the count rate of your instrument depending on the resolution. And basically spin echo is the way how we break out of this. Because if the count rate is too slow, the experiment becomes impossible. So thank you again. I'm sorry for being a little late, but